Welcome to day 23 of the Advent of Code. Today almost broke my spirit because my beautiful functional approach for part 1 worked perfectly, and then for part 2 it didn't scale at all. It would have taken an estimated 10,000 years to complete, so I had to resort to imperative mutation of Java arrays to get the runtime back to about half an hour. Okay, so what are we given here? So we're given a list of 9 numbers, which represents labeled cups, which are arranged in a circle. So you can think about it, 3, 8, 9, 1, 2, 5, 4, 6, 7, and then we repeat here. But of course, in an implementation, there, we just have lists and vectors and stuff. We don't have circles. Okay, let me immediately show you the rules of the game. So if I execute this, and here's my personal example, how does it work exactly? What has to be done in each round of this game? So we have 5 numbers at the start. Let me mark them like this. So here's the first one. That's the current cup. Then we have 3 cups that we want to move somewhere else. And then we have the next current cup for the next round. 2 is going to be the current cup of the next round. Okay, and then we are supposed to move those cups somewhere else. Where are we supposed to move them? Well, we look at the current cup and then decrement the number. So we get from 1 to 0, but 0 doesn't exist here. We only have the numbers from 1 to 9. So we wrap around to 9, and 9 would be over here. So we want to move 8, 6, 5 after the 9. Or in other words, if you look at these 2 ranges, left range and right range, we simply want to swap them. So 2, 4, 9 goes to the left, and 8, 6, 5 goes to the right. And as a C++ programmer, that would be a single call to standard rotate with begin, middle, and end. But this is not C++. This is Clojure or Java. Okay, cool. So then in the next round, 2 is the current element. So we're supposed to move 4, 9, and 8. And 6 is going to be the next current cup. Where are we supposed to move them? Well, if we decrement 2, we get 1. So 4, 9, and 8 should be moved here between 1 and 2. Okay, and that's exactly what happens. The 2 ends up over here, 4, 9, 8 end up over here. Or if you look at those at ranges, left range ends up at the right, and right range ends up at the left. Okay, then the next case is interesting because now we don't have 5 consecutive numbers. So current x, y, z, and the next current is at index 0. That would complicate our implementation quite a bit. So I decided to normalize by moving these 4 elements to the front. So 6, 5, 7, 3 ends up over here, and the rest ends up over here. And again, that's a rotate of the complete range. So the left range ends up here at the right, and the right range ends up here at the left. Okay, I'm sorry, I can't stop thinking in terms of C++. Been doing it for too many years. Okay, and then we can do the actual work. Now we have the contiguous elements again. So 5, 7, 3 is supposed to be moved. Where is it supposed to be moved? The decrement of 6 is 5. We can't use that because 5 is one of the moved cups. So we pick 4 as the destination cup. So 5, 7, 3 ends up after 4, as you can see here. Right, and again, as the ranges, that would be those 2 ranges. Left range ends up at the right, and right range ends up at the left. Okay, and you can look at more examples, but these are the 3 interesting cases. So here we have the current and the destination in that order. Here we have the destination and the current in the opposite order, and here we have the split case. Okay, so I abstracted this in this diagram. So I wrote 10 indices from 0 to 9 as opposed to 9 values from 1 to 9. That just makes the examples here in the comments a bit more interesting. And then I marked some of these indices with C for the current cup, which I call current index in my implementation, X, Y, Z for the moving cups, D for the destination cup, which is called dest index in my implementation, and N for the next current cup. And here's the case where C comes before D. Here's one example, one abstract example of that. So what do we have to do? We want to move X, Y, Z to the right, and we want to move N, 6, 7, D to the left. Right? And then you can look at that and figure out which indices from begin to end up where, and then you just call system array copy a bunch of times. But it's much more important to be able to, paint these diagrams yourselves or write them yourselves based on concrete examples. Okay, here's the other case where D comes before C. What do we want to do? So X, Y, Z should end up over here, and 2C should end up over here. So in effect, we have swapped those two ranges as we did here, right? And the rest at the left and right isn't touched by our algorithm. Okay, and then the split case where C, X, Y, Z add is not contiguous. In this example, it splits after CX. We want to move CX to the front, and we want to move everything else here to the back. Okay, cool. So just figuring this out took probably the most amount of time, and then just implementing those with a bunch of system array copies. Okay, what else do we have? So I have a long array for the moving cups. So X, Y, and Z are stored here temporarily. I don't want to, create new arrays all the time. I use one global array for that. Would be bad for multi-threading, but you can't multi-thread that solution anyways. Okay, and then I wrap that array in a sequence, and then give a type hint for async, because that makes Java interop much faster. And then I have a second array for this split case. So in the worst case, I could have C, X, Y, Z, but not N here, and then I would have to move 4 elements to the front, and that's why this array is a bit bigger. Okay. And note that this sequence always reflects the current state of the array, so I don't have to create new sequences. I can reuse the same sequence over the same array. I did this out of fear of performance, but I never measured this. Maybe you can try this out if it's really a performance bottleneck to create those arrays all the time. Okay, then this was the biggest performance improvement. So first of all, I implemented my own version of index of in Clojure, because Java doesn't have index of for arrays. It only has binary search for sorted arrays, which isn't useful here. So I did it with normal Clojure code. But then when I discovered this array sequence, the index of was much faster, because it's implemented in native Java, but I'm not exactly sure. Probably less overhead, less casting, less boxing, unboxing, and so on. Yeah, so that made my solution 3 times faster. That was quite a breakthrough. Okay, and then here is the function that computes the destination value. So for example, here it maps 1 to 9, or if you give 1 into the function, that then gives you 9 back. And here from 2, it gives you 1. And here from, what was that, from 6, it will give you 4, because 5 is already in the moving cups array. That's what happens here. So decrement the value. If it's 0, then wrap around. And if you can't find the element in seek moving, then we're done. Otherwise, we have to recur and keep decrementing. Yeah, should be straightforward. Okay, and then comes the meat of our solution, the 3 abstract cases that I explained before. So here's the case where the C, X, Y, Z is split somewhere in the middle. So what do we have to do? We have to store the CX somewhere else. Then we can copy the rest here to the right, and then we can copy the stored CX to the front. Right? And then you just have to figure out the correct arguments to system array copy. And this print line prints out the intermediate values here for demonstration purposes. Okay, so if that's not the case, then we know that C, X, Y, Z, N is contiguous. So what do we have to do then? We compute some temporary values. For example, here I say that X is 1 to the right of C, basically. That's what you see here. N is 4 to the right. That's correct. And then this is what copies the moving cups into our temporary array. So maybe this is a good idea to explain system array copy. So this is the source array. This is the start where you want to copy. This is the destination array, and this is the start where you want to, copy into the destination. And how many elements do you want to copy? So basically, yeah, what I just said. Okay, and that's a little hack that I use because I just want a single let binding for 6 bindings or names, and in the middle I need a system array copy, so I simply ignore the result of system array copy because it returns void in Java, and that is mapped to nil in Clojure. Okay, I do that because here I need the x, which is bound here, and for the next function call I need moving to contain the 3 moving cups, and that's why I have to do it here in between. Okay, so we compute the destination value. That's not so expensive, and then finding the destination index is quite expensive because in the worst case we have to scan the entire array. If you know of the faster way to do that, please let me know. I couldn't figure it out. Okay, and then the so-called destination index. Let's look at an example for the destination index. Yeah, so that's not the index where we copy x, y, z. X, y, z are copied after the destination index, and that's why it's a good idea to also have a value for the incremented d, basically, so where x is supposed to end up after all those movements. Yeah, that's why I also compute that. Okay, and then we have to distinguish between our two cases. So here we have the case where the current index is smaller than the destination index, so c comes before d, same diagram as above. So the xyz was already copied into the moving array by this system array copy, so we don't have to do it again. Then we can move the n6, 7, d9 over here, destroying the xyz, but then we can restore that by the last system array copy. Yeah, and again, figuring out these arguments is a lot of fun. Yeah, okay, and here's the other case. Again, xyz was already copied, so we can partially destroy it by copying 2c here over the yz, and then we can restore xyz by copying it here. Right, but again, these diagrams are probably a lot more revealing what's happening than those explanations of system array copy. Okay, so I think this is really a good example for using comments in your code, which I rarely do, but for these cases it makes it much more obvious what is going on. Okay, so in part 1, what do we actually have to do? So we start with the circle, our 9 elements. Current index starts at 0, steps starts at 100. Then we print, here intermediate lines to make it more obvious what's going on. And then if there are still steps to do, we call the step function with the current index, and whatever that returns, we use for the next current index, right? For example, here the next is returned. That then becomes the current index. Steps is decremented, and sooner or later we should end up at 0, and then we can prepare the result and use for our performance. So what do we want for part 1 as a result? So we have to look at the last iteration of the array, and then after the 1 we have 4, 5, 9, 8, 3, 6, 2, 7. That's our final result, 4, 5, 9, 8, 3, 6, 2, 7. And we simply compute that here. We search for the index of the 1, so we would find that here. Then we call split at, which gives us everything before the 1 in the back sequence here, and then everything starting at the 1 in the next sequence, which I destructure for the 1, which gives us the 1, and then front gives us everything after the 1, and then we can simply concat front and back, and then we get our nice little result here. Okay, cool. Not strictly necessary. A human can figure out I have to type this into the website followed by this, right? But I thought that this was a nice exercise in destructuring, nested destructuring. I love to do that. Okay, and then for part 2, the initial steps are kind of similar. The destructuring is a bit different because we're only interested in the 2 elements after the 1, which we're supposed to multiply. Okay. Right, and then you can see here I commented out the computation for part 2 because it took 1900 seconds, which is just above half an hour, 31 minutes something. Yeah, and why is it so expensive? Because we don't have 9 elements. After the 9 elements, we have in additional elements to make a total of 1 million elements. And then we don't perform 100 steps, but 10 million. And that's what broke the performance of my functional solution. Yeah, and again, I think half an hour is not extremely efficient, but at least, I can take a shower, and when I come back, I know the answer. Okay, and here you can see just the setup for part 1 that I already explained. So it was an interesting performance puzzle. I'm not sure if half an hour is the best performance. Maybe there's some kind of data structure that is optimized for these kind of operations. If you know of such a data structure, please let me know in the comments below, or however you solve this problem in an acceptable time frame. I'm extremely interested in your approaches.